Hi folks, Mr. Ackerman here. Thanks for watching. The topic of this video, as you can see, is projectile motion part 2. So this is the continuation of the video that maybe you just watched. Previously in part 1 we dealt with projectile motion where the launch of the projectile was horizontal. So think a ball rolling off the edge of a table, or a gun being fired which is being held out straight in front of you, horizontal to the ground. In this video we're going to look at a more general case where a projectile could be launched at any angle. It could be launched above the horizontal, so now think of a golf game. At least if you're a decent golfer, unlike me, most of your shots hopefully go up rather than straight down. But anyway, that would be one example. There are examples of launching straight down. For example, if you are up on a balcony, for example, and you're throwing paper airplanes off of the balcony, you might launch one of them sort of on a downward angle, so that would be a non-horizontal launch. So we're going to look at how you do your calculations for these kinds of launches, and I think you'll be happy to see that they're actually really just an extension of what you learned in video number 1. We're going to finish off with an interesting application which anyone who's interested in sports will appreciate, especially if you like the game of football. And I'm thinking of American football this time, not the one that we call soccer over here. Anyway, just to move things along, let's take a look at where we are in the schedule. We are currently in Lesson 3 still, Section 1.4 of the text. We're now on the horizontal launches. We are working on pre-lesson reading number 3 over here, paying attention to sample problem 4 on 47. And in class, we'll be doing this part here, non-horizontal launches, 9 and 10 on page 50. Also, you might be interested in going to a website I introduced you to in class. It's PhET. It's a great website that has simulations for projectile motion. And if you just go in there and you click on this link, or if you just go to the website, go under physics and search under projectile motion, you can actually play around with a simulation of a projectile motion launcher to help you see what's going on in these kinds of questions. Also in class, we're going to see a video called The Physics of Football. This is, I think, one of the only videos I use throughout the course that's not, at least on YouTube. This one I have on VHS from ancient times, and so you're going to have to come to class to see that. After class, you can try a few questions over here, 5 and 6 on 51, and that is about all I have to say to get us started here. So let's close out the front screen and get started with a little discussion on non-horizontal launches. So basically, what's going on here is we're talking, for example, about a launch, let's just say, above the horizontal. So I'm going to draw in my x and y axes like this, and I'm going to imagine that there is a launch that has occurred, let's say like this. So this will represent the initial velocity vector, and we would have theta as our launch angle. The velocity would be v1, so it would have some sort of magnitude, it would be on some sort of angle. And how does this differ from horizontal launches? Well, really the only difference is that in addition to an x component for velocity, this is the initial velocity in the x direction, which by the way you know is constant, there's also an initial y velocity, and so we'll call this v1 in the y direction, and these meet at a right angle. Now of course, v1 in the y direction is not constant. If you recall what we learned earlier, in the y direction we have acceleration. We have acceleration of 9.8 meters per second squared down, which means that the initial y velocity will not stay constant, it will change. It will change in the downward direction at a rate of 9.8 meters per second every second. So assuming positive y and positive x, that means negative y is down this way, so this is actually going to be a negative number here. And in the example I've used, v1 in the y direction would be positive. Now I think you can imagine if you launched a projectile like this, it would follow a certain path that would have it rising initially, and then as a result of gravity coming down. So if we just extend the black line that runs through here, this might represent the ground, then you can see that we have a number of variables that we can measure here. For example, the total distance that the projectile goes in the x direction, we call that the range. The horizontal range is what it's sometimes called. So there you go. That is the, whoops, let me try that again. Horizontal range. Sorry, I'm having a bit of trouble today with my letters here. Let's erase that. Make that a nice Z. There we go. Horizontal range. Okay. Of course, we have a maximum height. We never had to deal with that before because the ball never went up. It only went across and then down. So that would be how high above the ground. You would measure that by measuring a delta D in the y direction. We also have when the ball lands, in other words, at impact, we can discuss how long it has been in the air for. So delta T, also sometimes called the hang time. Those of you who watch American football have heard the term hang time, how long the ball stays in the air when the kicker kicks it. And of course, other variables such as the impact velocity would apply. That would be the velocity at the moment of impact, and we could talk about the velocity at any other time. This is the introduction. Let's actually see how this stuff works by taking a look at a problem in your textbook. So I'll close out this screen here, and I'll open a new one. The question I'd like to look at is number 9, and this one is on page 50, I believe. Yes, it's 9 on page 50, and of course we're talking about the Physics 12 book by Nelson, for those of you who want some sort of reference, and also to give credit where this, for where this question came from. Anyway, let's have a look. A cannon is set to fire 45 degrees above the horizontal. It leaves the muzzle with a speed of 220 meters per second. They ask you to neglect air resistance. Determine the cannonball's maximum height, time of flight, horizontal range, and velocity at impact. So as you know, rule number 1 in physics, always start with a diagram. So here's where I'm going to draw that. Maybe I'll put in a y-axis here. Okay, and here is my, whoops, here's my x-axis. There we go. I'm going to call this the positive y direction up, and this is going to be the positive x direction to the right. And just like before, I'm going to have my initial velocity vector. Now they mentioned something about 45 degrees here, so I can put that in. And I can predict that this cannonball will rise up and it's going to come down maybe somewhere over here. So right away I can start to see things like the delta dx, the horizontal range, which goes over to there and over to here. That would be question C, right? They ask for the maximum height, and I can see that that will be somewhere around here. Maximum height. That'll be a delta dy idea. They ask for the time of flight. That will be the time when the projectile lands right about there. And they also ask for the velocity at impact. Here's where the impact is. So I'll just write that word in so that you remember. And if you recall from yesterday's or the previous lesson that you were watching on YouTube, the path of the ball as it moves along in this parabolic path, the velocity vector has two components. It's got an x and a y component. Now, in the beginning here, you can see that there's a little bit of a y component, and there's also a little bit of an x component. So we call that v1 in the y direction, and here's v1 in the x direction, although that is constant. That same thing will happen at all points throughout the path, even at the end. So even at the end, there will still be some x component, which, by the way, I think you know Vx is constant, so that's going to stay the same. But there will also be some sort of downward y component, and if we draw those together, we start to get an idea of what would be the overall, or what they call the tangent velocity at impact. That would be the sum of the x and y components, And that's what they're talking about in part D, the velocity at impact. How do the Vx and the Vy go together to form V at impact? So keep that in mind for part D. Okay, we're ready to get started on the actual calculations. How do we do this? Well, first of all, we're going to need to know about the components. So see if you can figure this one out. Pause the video if you want, but I'm just going to continue on here. Vx, they tell us 220 is the initial velocity's magnitude, 220 meters per second. So that means I know that Vx is 220 cos of 45 degrees, which I've worked out here in advance this time, so I could be prepared. It comes to 155.56. And a whole bunch of other digits. And Vy is 220 sine 45 degrees. And just by coincidence, because sine and cos of 45 are actually the same, these numbers are the same. That's not always going to be the case. At a 45-degree angle, you're kind of going right down the middle there, so the components are equal. Anyway, what do we do with these numbers? Well, let's write down what we also know. A in the y direction is 9.8 negative meters per second squared. These are the things that we know are true. So for part A, what do you do? Well, they're asking for the maximum height. So this is kind of like asking what's delta dy when we're at maximum height. Well, let me think for a moment. How do you translate this English statement into a math statement? Well, do you remember from grade 11 style problems, when a ball rises up vertically and it reaches its maximum height, something happens, and that something is that the y velocity becomes 0 because the object stops rising and it begins to come down. So what they're doing is they're planting some implied information in here. They're asking for delta d when the final velocity is 0, given the initial velocity in the y direction was this, and the acceleration was that. So what we've really got here is a question involving the initial Vy, a final Vy, a delta d, and an acceleration. And if you think about what equation would be ideal for that, I think you'll see that this one fits the bill. We want to solve for delta d, and we know the acceleration is negative 9.8. V1 is this in the y direction, and we're going to square that, so we've got that information. And this, of course, is 0 because we're at maximum height. So on your own, try solving this. I think I've done enough for you. Now it's your turn to take over. I think if you do this, you will find the maximum height. Not a problem. Okay, let's take a look at part B. The time of flight. So they want us to know delta t when the ball lands. Well, again, you have to translate an English sentence into math ideas. Here's some math ideas, but when the ball lands, how do I make that into a math idea? That's over here. Well, what for sure happens when the ball lands? A lot of students jump up at this point and they say, oh, well, the velocity is 0, because anytime a ball lands and hits the ground, it stops moving. And that's kind of true. It's not always true. A ball might land and roll. So in my opinion, the idea that when a ball lands, the velocity becomes 0 is not really a good way of thinking about this question. We need a better condition that no one can disagree with, because then we'll know we have it correct. When the ball lands, I'll tell you something that happens that's for sure. In this case, because we're dealing with level ground, the ball returns to the height that it started at. You can see from the diagram here, this is why you have to draw diagrams, because otherwise you can't see what's going on. You can see that when the ball lands, it is definitely, without any argument, back at the same vertical position that it was at when it started. So when the ball lands is this idea, delta dy equals 0. That no one can argue with. And so that's what we're going to use. We have a delta d of 0 implied. We have Vy initially this, Ay that, and they want delta t. So what is a good formula? Well, I think if you solve this one using delta D equals V1 delta T plus a half A delta T squared. Let's see, here we're going to use 0, so we know that. V1, make sure you use your y velocity initially, so we've got that. Delta T is what we're solving for. A we know, it's negative 9.8, and there's delta T again. Now notice this time you've got a quadratic on your hands. And if you solve this, you're going to get 2 solutions, which means the math is telling you that there are 2 times when the ball is at the ground. Does that bother you? It shouldn't. Here's one of them, the impact, but the ball started at the ground. So one of your answers here, if you solve your quadratic correctly, will be 0, and the other one will be sometime a little while later when the ball returns to the ground. We expect to get 2 solutions. It makes sense. Okay, moving along, I see I've run out of space over here, just about. However, let me see if I can pull this up here for a sec and get a little bit more space out of here. Where am I going to put that? There we go. Bear with me, folks. C. What is the horizontal range? Well, the horizontal range just means how far did you travel horizontally in the time that it took to get back to the ground. Well, we already know the time it took to get back to the ground. You're going to solve for that in part B. And you also know that your Vx is constant, so you move horizontally at the steady rate of 155.56 meters per second all the way. Well, what's a formula for constant speed and displacement? It's easy. It's delta D, this time in the x direction, equals V delta T. And just remember, these will have x's underneath them. This is an x idea, a horizontal range question. So since you know Vx and you know delta T, you got that back here in part B, just sub in and solve. What they're basically asking here is to find delta D x when delta T is the same as what we had here. So basically at the landing time. Okay. That leaves me with not enough room to do part D, so I'm not going to do it. No, just kidding. I am going to do it. I just have to find another layer to do it on. So let's close this out and go to here. Here we're going to do part D, so let me just write that in here. Velocity at impact. And if you remember, at the very beginning of the analysis here, I told you a little bit about the velocity at impact. Let's just go back in order to see what that was. Do you remember when we were talking about this? We talked about the initial velocity vector components and how the Vx stays constant, but the Vy changes. The Vy changes because there's acceleration in the y direction. Initially it's up, but as time goes by, it starts to turn down. And we discussed how you need to combine these two to find V impact. So how do you do this? Well, first of all, we know the initial 2 components. And from part B, you know how long this whole thing lasted for. Therefore, using time, you ought to be able to figure out what is the new Vy. Because remember, it changes by 9.8 every second. And you know that Vx is constant, so can you put these two together? What's it going to look like? Here's what it's going to look like. You're going to have your Vx, which is constant, at 155.56 repeating. And then you're going to have a Vy that you don't know at this time. All you do know is that if you go back to part B, you know the time. And if I sneak a peek at the answer in the book, if I recall correctly, the time is something like 32 seconds. Okay, you should solve this using with your calculator. I think it's actually with decimals something like 31.74 seconds. I'll just write in here C part B. Okay. And of course we know AY is negative 9.8. Therefore, give me V2 knowing what V1 was and knowing that for some time some acceleration occurred. Okay? So you can write it like this if you want. V1y is positive 155.56 if I remember correctly. A is negative 9.8. The time is 31.74. That's going to give you a number here which, lo and behold, is actually the negative of what it was when the question started. See if you can figure out why. If you remember in the beginning, it started off at positive 155.56. Now it's negative 155.56. I wonder why that is. We have done questions where a ball has returned to the same vertical position that it started from, and its upward velocity has transformed into the same downward velocity, same magnitude, but down. So anyway, put these two together. It should come out to 155.56. I'm leaving out this negative because I'm showing a downward arrow here, so it's pretty clear. How do we connect these two? Tip to tail. There you go. So this here is your V instantaneous at impact, or what we sometimes just call the impact velocity. Of course, there's an angle theta below the horizontal. How are you going to solve this? You guys know this. This is old information. You're going to find the magnitude using Pythagorean theorem, like you always do with vector components, and you're going to find the direction, the angle theta, using trig. I think here you can use the tan ratio because you have the opposite side and you have the adjacent side. Okay? And that's basically how you solve these questions. You convert the English statements into math statements and you use your kinematic equations to solve. Just remember, you can never, never, never mix x's and y's in an equation. All the equations I've used here always have y values, or they always have x values, such as in the range equation here. Okay? I apologize, I didn't write them down here when I did this the first time, but these are y's because this was a vertical question. Okay, so those, you should go back in there and put those in, and the same with this. These should be y's as well. You cannot mix x's and y's in the same equation. The only thing that is usable in both formulas, of course, is the time, because time applies the same to x and y direction. Okay? So I hope that helps you with solving the equations, and so, or the questions rather, and so I'm going to leave you with an interesting application. This application, you'll have to turn in your book to close to the end of the section. In fact, if I show you here, it's on page 49. Whoops, jumping around there. Here's page 49. And you'll see they go through an argument here where they argue that if the ball or the projectile lands at the same height from which it was launched, in other words, like a game of American football or golf or something like that, then you can write these equations. I'm not going to go through it with you. You can follow along on your own in the text. But if you go through this, you end up with two interesting results. And I've cut and pasted the two equations in here. It says that there's a formula for the amount of time that the ball spends in the air, and there's also a simple formula for the range. This is known as the hang time equation, and remember, it's only the time if the ball lands at the same height from which it was launched. And this is the range equation, again, only if the ball lands from the same height from which it was launched. So I'm going to put that in here because I don't want anyone using these equations unless they are absolutely entitled to it. People make mistakes with these, so only use if ball lands at same height from which it was launched. If I could get that flashing on the screen here, I would, just to make sure that you don't use this incorrectly. Okay? So that's the first thing with a little bit of a warning. Now, why do I want to show these to you? Because they have an interesting application in sports. Take a look at especially the range equation. This is the cool one. If you have taken advanced functions, or even functions and relations, you probably know how to deal with sine of 2 times an angle. It just means multiply the angle by 2. So look what happens here. When you have sine 2 theta in your formula, check out what happens if the launch angle, for example, is, 30 degrees, let's pick. Well, so according to this formula, I punch in 30 degrees, and I'm going to get sine of 2 times 30, which is the sine of 60 degrees, right? And if you punch sine of 60 into your calculator, I think you get something like 0.866 or whatever. Okay? But watch what else happens. If I put in the sine of 60 degrees, I will get the sine of 2 times 60. That's the sine of 120. Punch that into your calculator, and what do you get? Surprise, surprise. You also get 0.866. Since the only other two things in this formula are v1 squared, which is a constant for any given launch, and g, 9.8, what this formula is telling you is that there are two launch angles that give you the same range. Interesting. It's kind of like this picture that I have for you here. Here, this is a picture I got off YouTube, off of Google Images. Unfortunately, I don't know who made it, so I thank someone out there. This shows what's going on. It's a projectile launched at 30 degrees with a certain speed and 60 degrees at a certain speed. 60 degrees goes higher, 30 degrees goes lower. They both have the same range when they return to the same height. Interesting. Just to go back, what would be two other angles that would do this? I'll give you a hint. Suppose you started with 15 degrees. Okay. You'd get the sine of 2 times 15, which is the sine of 30, and the sine of 30, of course, is 0.5. What other angle would get you 0.5 for its sine ratio? I'll let you pause the video and think about this. Okay, now we're back. The angle is 75 degrees, and here's why. The sine of 2 times 75 is the sine of 150, and the sine of 150 is also 0.5. So hey, there's another two angles that together give you the same range, just like in this picture. I just don't have a picture for the 15 and the 75. Can you see what the rule is? Give you a moment to think about it. Any two acute angles that add to 90 degrees give you the same horizontal range, which is kind of cool, because if you're playing football, that means you could, for example, kick the ball at the high angle, 60 degrees, and it'll go just as far down the field as if you kick at the low angle. So why would you pick one angle or another? If you're the quarterback who throws the ball in a game of football, you have a choice of picking two angles to hit your receiver, the guy who runs and catches the ball. Which one would you pick? Well, I'll leave it to you to think about this. If you were playing sports, which one would the kicker choose in a game of football? The high angle or the low angle? And which angle would a thrower choose? The high angle or the low angle? Is it possible that the thrower and, sorry about the announcements that are coming on here, we're just changing periods, but would the kicker always kick at the high angle or always at the low angle? Would the thrower always kick at the high or the low angle? When would they choose what? Think about this and we will discuss further in class. Just one thing I will let you in on, a little secret here, or maybe it's not a secret. While there are two angles that give the same range, right? When you plug these into the hang time formula, notice how you're either going to end up with sine of 30 or you're going to end up with sine of 60. 2 is a constant, the initial velocity magnitude is a constant, g is a constant, Sine of 30 is not equal to sine of 60. These are not equal, which means the times will be different. In fact, maybe you can see the sine of 30 is less than the sine of 60. Therefore, for the 30-60 option, they both have the same range, but one goes higher. It stays in the air longer. It's got a longer hang time. One stays in the air less time. So think like a football player. When would you want the ball to get to where it's going quickly, and when would you want it to take more time? These are some important hints to think about when you're analyzing the practical application of these two equations. All right, that's about all I have for you. We will talk later in class about one more thing, and that is the effect of air resistance on the ball, or the projectile, and that's why you want to come to class to watch this cool video here, The Physics of Football, where some actual NFL football players and a scientist will get together to analyze what's going on in the game of football as far as projectile motion is concerned. All right, folks, thanks for watching. I will see you on another video. Have a good day. Take care.